Hello and welcome to this video lecture. So for this video lecture, we'll just be continuing with the discussion of the Laplace transformation, but I'll be working through several examples of how certain things transform from the time domain into the S domain. So I'll just kind of reference that by saying that we're going into this example. And so I'll keep it on the same OneNote page that I've been working on so far. So I'll just preface that by saying, okay, let's see how this works. And I think you're going to be pleasantly surprised here in a moment or two. But let's go ahead and cover kind of the most obvious things that we've been discussing associated with the Laplace transform. So let's go ahead and take the Laplace transform, or find the Laplace transform for the derivative of a function. So, of course, for us, that would be the Laplace transformation of df dt, and that's going to be equal to integral from 0 to infinity. Now, I'll mention something here in just a second, but let's go ahead and just write down the transform. E to the negative st, and then the function that we are working with is the derivative of some function. So we just plug that in for the function, and we go ahead and find the Laplace transform for it. Now, one thing that I want to note is, in particular, the Laplace transformation that I've introduced here and that we will be using in this class is called what's called a single-sided Laplace transformation. And there is a little technicality that I haven't really gotten into, which is that we're really going from t0 minus to infinity. So that's what we're really doing here. So what that means is that just a little hair on the negative side of 0 is where we're actually starting. And this is called a single-sided Laplace transformation. That's what we're going to be using throughout this entire class. Now, you can have a double-sided Laplace transformation, which is from negative infinity to positive infinity. That's used much less frequently. So when people say Laplace transformation, they almost always mean the single-sided Laplace transformation, kind of on this positive side, up to positive infinity. But nonetheless, you have to be a little bit careful. So if you're talking to somebody about a Laplace transformation, or you're using a reference or something like that, you really need to make sure that they're talking single-sided or double-sided. I've never seen the negative side of the Laplace transformation, but there's no reason why you couldn't have a transformation like that. I don't know if it'd be very useful, going from negative infinity to 0 plus. So I just wanted to mention this little minus here. I'm never going to write it down. I'm just going to say it this time, and then we'll just go ahead and remember implicitly that we're actually going from 0 minus to infinity. And so again, for this class, we're going to be working with the single-sided Laplace transformation. But again, if you're using references and things like that, you need to kind of check in with that reference and see what's going on. So with that, let's go ahead and work with this transformation. Now, the easiest way to work with this particular, or at least I think it's the easiest way, is to work with integration by parts. And just as a little reminder, integration by parts is integral from a to b of u dv is equal to uv evaluated from that very same a to b, minus integral from a to b of v times du. So there we go. So let's go ahead and start mapping things over. So we have our u, and so we can probably see that that corresponds to our exponential function. And yeah, that's kind of nice. We have this dv, and so why don't we go ahead and map this dv to the function that is the derivative of some other function. So we can say that u is equal to e to the negative st, and we can say then, since v or dv is mapped, or we're going to just say is equal to that derivative, then v is just equal to the function itself. So we can say that v is equal to f of t, which of course is equal to the integral of df dt. So we can clearly map those into place. Now, one other thing that we need, of course, is our du, because that's appearing over here. And so clearly that du is just simply negative s e to the negative st. So with that, we can go ahead and plug all that into this expression for the integral using, or integration working with by parts, or integration by parts might be a better way to say it. And so then we get integral 0 to infinity. Again, technically 0 minus to infinity. I'll just mention that a couple times throughout. And then we have our original integral for the transformation dt. And that's going to be equal to then e to the negative st f of t, evaluated from 0 to infinity, plus then, because remember we got a minus up here, and then we have our minus right here. So we can just go ahead and combine those together into a plus s integral, because remember s is not a part of the integral. We're integrating with respect to t. And then we have our u, negative e to the negative st. Oh, my apologies, that's part of du. E to the negative st, and then we have our v, f of t, and then of course we have our dt, and that's also part of the mix. So going ahead and working with this, what do we have? Well, let's take a look at this first term here. And then for the first term, we have when t is equal to 0, because we have a lower limit of integration and an upper limit of integration. When t is equal to 0, we have e to the negative st f of t is clearly equal to, well, this exponential function. When we plug in t equals 0, we're just going to get a 1. So we'll get a 1. And then we just plug in t equals 0 for our function. And so we get f of 0. And clearly that's just equal to f of 0. And you can see why I called this a one-stop differential equation shop. Because just out of this transformation, what did we suddenly get? We suddenly got the initial condition for our function, whatever that function might be that we are taking the derivative of. We have the initial condition right there just coming on out. So the initial condition is captured. Now, at t equals infinity, we have e to the negative st times f of t. And so we may be looking at this and going, oh my goodness, what in the world do? We got this e to the negative s infinity effectively and t infinity. Well, t infinity is just going to be what we would call the steady state value of this function if it ever goes to a steady state value. or it could kind of keep growing, in which case it never reaches a steady state value. And so what does this do? I mean, this just seems kind of impossible to deal with. Well, and that's the entire reason that we have this idea of exponential order. Because yeah, you'd be stopped dead cold on this if you didn't just say, fine, we're only going to choose functions of exponential order. And as long as we only choose those functions or work with those functions, this will go to zero. So you can kind of see where this whole idea of the limitation associated with going to exponential order came from. Some mathematician got to this point and was like, oh my goodness, what do I do with this thing? And then they're like, well, we don't know unless we impose this limitation. And then it's like, okay, then we can move forward. Great. So, one of the things I want you to see from this class is that we generally as engineers have this picture of math being this this beautiful construct that is completely perfect in every regard, and there isn't an issue associated, or there isn't there aren't these issues associated with math like, oh yeah, well, we can't quite work with this or we can't quite work with that. No, that's embedded in math. And so somebody hit this, they said, wow, I don't know what to do with this. Well, okay, if I do this, then I can keep moving forward. And so fine, okay, let's do it. So let's go ahead and say, okay, we're only going to work with things of exponential order, and we're going to call it good, and we're going to move forward. Now, of course, folks, I'm sure, tested this idea of exponential order to see if there were other looser limitations that could be applied to it. And my guess is they couldn't find any, so they just went ahead and stuck with this whole exponential order idea. So yeah, they had a stumbling point, and they just said, fine, what does it take to get past it? And they got past it, and that's it. But they had to buy themselves a limitation in order to get past that. So you can kind of see where things aren't this perfectly beautiful thing. It's like, oh goodness, we got this thing. And so then they just did this inelegant thing of, fine, you can't use these Laplace transforms for functions that don't meet this particular requirement. And that's it. So hopefully that gives you a bit of a better understanding of why we have this idea of exponential order, because otherwise we would have things that we couldn't work with. So let's go ahead now and work with the second one. And what can we see? We can see that part of the second one, I'm not going to address this S here up in the front. We're going to just hang on to that S. But I am going to look at this 0 to infinity of e to the negative st f of t dt. And you'll recognize that as the definition of the Laplace transform of this function f of t. And that's just equal to f of s. So then plugging everything back on in, and of course, after that discussion, this may seem surprising, but because, the discussion kind of went on for a little while, but once you see it, it'll be like, oh, well, of course, that's exactly what we expected. And so what do we get? From the first term, we get 0 minus f, not effectively our initial condition, plus then s times f of s. And sure enough, there it is. We're taking the derivative. We just go ahead and we multiply the transform function by s, reflecting that we took a single derivative. And then the nice thing is we also were able to capture the initial condition. So generally the way this is written, of course, is f times f of s, which is something that we already knew from last lecture. I introduced it. I just said we got a derivative, we multiply by s, just like we saw with the characteristic equation approach, if I may call it that. But now we actually see it coming out of the formal definition. So completely expected result. We can see it from what we knew before, and now we can see it coming from this formal definition of the Laplace transform. So that's very powerful. Now, let's go ahead. So we have the derivative. We can now see that the initial condition is coming in as a natural part of the transformation, unlike before where we're like, okay, now we have to do this and now we have to do that and we have to account for these other things. Here you don't have anything to worry about. It's already taken care of. Now let's go to something a little less intuitive, at least on the surface, because we just haven't dealt with it. So let's take the Laplace transform for the integral of a function. So taking the Laplace transformation for the integral, we have L of the integral f of t dt, and that's equal to the integral from 0 to infinity, again, technically 0 minus, e to the negative st times the integral f of t dt, all that times dt. Now, you may already have a guess as to what might be happening. And that guess would probably be correct for the most part. At least in the most general sense, we haven't really captured what's going on with the initial condition, and that's, or what we could call the initial condition. But for the transformed function itself, we can understand that in calculus, taking the derivative is the inverse of integrating something. So if we take the derivative of something in the time domain and it maps over to multiplying by s in the frequency domain, and taking the integral is the inverse operation in the time domain, well, what's the inverse operation in the frequency domain? Well, if multiplying by s is the derivative, dividing by s or multiplying by 1 over s should represent taking the integral. And if that's what you're, because of course, dividing by s is the algebraic inverse of multiplying by s. So if that's what you were thinking, you're actually spot on. So let's go ahead and, again, using integration, by parts, what we have now is I'm going to let u equal the integral of f of t dt. So now u will be tied to the function rather, or what we're doing with the function rather than tied to the exponential function like it was last time. I'll let v now capture what's going on with the exponential function, integral e to the negative st dt. And so when we go ahead and work through all of that, we could do a quick little substitution if you wanted. We could say, okay, let's use, since we're using v's and u's, let's go ahead and, this is just a little aside in case you're having trouble remembering, we could say w is equal to negative st, dw is equal to negative s dt. And so then we could see that dt is equal to negative 1 over s times dw. And we could substitute that on in. And when we do, of course, and then integrate, because then we'd have e to the u times, e to the w times dw, and then that's just e to the w. And then we back substitute in for negative st. And of course, associated with that dw, though, is the negative, and we can see it coming into play now, that negative 1 over s. So we would get negative 1 over s, e to the negative st. And then last but not least, of course, du. So if u is equal to the integral, then du is just going to be the function itself, f of t. So, and sorry for squeezing that in there, but I think you can see it relatively well. So then going ahead and plugging all that in, we get the integral from 0 to infinity of e to the negative st integral f of t dt times dt is simply equal to, and here I'll kind of do the equals down here, but you know, with the integral notation, things kind of get a little bit fat there in the line, so I'll go ahead and just skip a line there. And we have integral f of t times dt, and all that multiplied by our negative 1 over s e to the negative st. And then we'll evaluate from limits of integration 0 to infinity. And then we'll have, we'll go ahead and go with the plus. We'll have plus, then plus integral 0 to infinity of f of t times 1 over s. So you can see we had a negative out here. We had a negative time multiplying the 1 over negative 1 multiplying the 1 over s. So I just went ahead and canceled those out. Ended up with positive. Well, I shouldn't say canceled it out, multiplied it out. E to the negative st times dt. And so going ahead, and of course, this latter one is coming from RV right there, and then we also have our du coming in. So this is our v, and this is our du coming in right there. So now going ahead and looking, so let's initially look at this first term right here, just like we did before. So we have at t equals 0, we have negative 1 over s e to the negative st times the integral of f of t dt, all that evaluated at t equals 0. And so what do we get? Well, this e to the negative st is going to be what? That's just going to be a 1. And so then we're just simply left with negative 1 over s times the integral of f of t dt simply evaluated at t equals 0. So we have to go ahead and integrate f of t, then whatever function we get, we plug in t equals 0, we take that value, because it has to be a value, we take that value and we multiply it by negative 1 over s, and we just go ahead and run with that in the transformed equation that we're dealing with, or transformed relationship that we're dealing with. Additionally, at t equals infinity, we have our negative 1 over s times e to the negative st integral f of t dt. And of course, we end up in that same quandary that we did before. What in the world does this thing do? And as long as we apply the limitation of exponential order, what can we see? Well, if we're taking the integral of exponential functions, which are kind of the limiting function for exponential order, if we take integrals of exponential functions, what do we get? We just get more exponential functions. And so we should be able to, again, work with the exponential order argument for even the integral, and we should be able to say that this is equal to 0. Again, using this exponential order argument. So that takes care of the first term. Now for the second term, we have integral 0 to infinity. So understand we have this 1 over s. We can go ahead and factor that on out. And if we do, then we're just left with, and this shouldn't be a surprise. Let's do it this way, though. Let's go ahead and write this e to the st in front of the f of t dt, just to make the form exact for, of course, as we would expect. That is nothing more than the Laplace transform of the function itself just coming right on through, the function that we're integrating just coming right on through. And so just as we would expect, now again, the initial condition, or capturing what's going on with the initial, maybe I'll say value in this case, for the integral, is a little bit different than it was for the derivative, but it's not too bad. Not too different. And so then we have 0 minus this negative 1 over s times integral of f of t dt, all that evaluated at t equals 0. So we have that, and then we have our minus. Actually, in this particular case, I think I already canceled. Yep, I already canceled out that minus, and so then we have our plus 1 over s times f of s. Okay, so writing it in a simpler form, here I'll do kind of a split line here. Clearly, negative cancels with the negative, and so then we're just left with a positive 1 over s. And so then we have simply 1 over s times f of s now plus 1 over s times the integral of f of t dt evaluated at t equals 0. And there we go. And so we can see exactly what we expected. We can see that multiplying and dividing algebraically are inverses, taking the derivative and integrating are inverses. So it shouldn't be any surprise that when we get over into the frequency domain, where we can deal with calculus operations in an algebraic fashion, it shouldn't be any surprise that these inverse calculus functions in the time domain map over to inverse algebraic functions in the frequency domain. Taking the derivative in the time domain leads to multiplying by s in the frequency domain. Taking the integral in the time domain maps over to dividing by s in the frequency domain. Or here we've represented dividing by s as multiplying by 1 over s. And so we can see how all of this works out, how we have these analogous structures, let's say it that way, when we're dealing with these. And what's really nice about the Laplace transform is if we were dealing with the integral in the time domain with a differential equation, namely we had what's called an integro differential equation, hopefully I said that right, boy, that would just really throw our minds for a loop. But here, because then we're like, okay, I have a function, and then I'm adding to that function a derivative of some order, and then in addition to adding that to the function, I'm also adding now the integral of that function, and all of that has to equal something. I mean, that would just blow our minds. And so, which is why we really haven't talked about them, though they do exist. But understand that, with this mapping into the frequency domain, we can handle these integrals without any trouble. It just goes across is now dividing by s rather than multiplying by s. I mean, that's not very difficult to deal with. So hopefully you can see how powerful this transformation is. But we haven't quite explored the depths of how powerful this particular approach is. And the reason I say that is because as you would have expected from our prior discussions, we have been able to transform calculus operations. Now, the integral might have been a little bit of a surprise because we hadn't talked about integrals before in our discussions of any of these other approaches. And so now we can start to see how powerful this transformation is, because it's able to handle these integrals when we really didn't want to bring them into the discussion before. But it turns out that this transformation is actually much more powerful than that. And we'll get into that right now. Because not only can we transform, and this is where things get really mind-blowing and really interesting, is we don't just have to transform calculus operations, we can actually also find transformations of functions, known functions. And so what does that mean? So here, let me write this down. So here, as using engineering speak, we would say, okay, we're going to find the Laplace transformation of various input signals. In math speak, that would be developing the Laplace transformation for various signals typically used as inputs. In other words, functions that yield. So now going into the math speak, functions that yield a non-homogeneous differential equation. Okay. So why is this so interesting? Well, let me discuss that after we do this first transformation. So the first transformation is one that we use all the time as engineers, which is the step function. And so why do I say that, or we encounter this and use it? Why do I say that we encounter it? Well, think about it this way. Let's say that we have some system that we are asking, or that we have asked to be at one value. So maybe it's I forget, not a flap, it's an elevator or something like that on an airplane wing. I may be misremembering it, but it's an elevator on the airplane, let's just say it that way, which is one of those control surfaces that moves up and down. And let's say that we had it at a particular angle for a while because we needed to do something. And then what is a step input? A step input is just simply, okay, we now need that control surface to change its angle. And so then we give it a step input. We say, okay, surface, go to a new angle. And that's what a step input is. That's what a step function is just saying, you're at this particular state, we want you to go to a new state, or new value of that state would be a better way to say it. So that's represented in the following way. So u is going to be the value of the function. T of course is time as we usually use it here for us as engineers. And so what we'll do is we'll allow this step function to go from 0 up to a value of amplitude A at t equals, effectively t equals 0. So here I drew it a little before just so that I don't confuse you with the black line and the blue line. So the way we can express this, so this is captured by the following. We have f of t is equal to 0 for t less than 0, and we have it being equal to a for t greater than or equal to 0. So let's go ahead and work with the Laplace transformation, or find the Laplace transformation for this particular function. So then we have the Laplace transformation of f of t is equal to f of s, of course. And so then we just go ahead and substitute on in this time domain function, 0 to infinity e to the negative st, and then we have a dt. And the wonderful thing to notice about this particular single-sided Laplace transformation is that we don't even have to concern ourselves with the fact that less than 0, the function is 0, because we aren't even integrating down there. So that function could be doing whatever, and for the single-sided Laplace transformation, it would be just, well, it doesn't contribute to the area underneath the curve of e to the st times a. So we don't even have to concern ourselves with that. So that makes finding this particular transform a lot easier, because you might have been like, ooh, how in the world are we going to deal with this thing? Well, thankfully, the single-sided Laplace transformation doesn't even have to worry about it. So here we can go ahead and define a u substitution. So let's say that u is equal to negative st, and of course you already saw this with the w that we were talking about before. And then we have du is equal to negative s dt. And then last but not least, here I'll just put commas here because we're just kind of moving on along through all of these. And then dt is of course equal to negative 1 over s du. And so then we can go ahead and, substituting all of that in, we technically get integral from u1 to u2. I'm not going to find what those are. I'm just going to back substitute in for the substitution before we find, or we work through finding those limits of integration. Then we have a times e to the u, and here I'll just reverse those. Remember, a is a constant, and then of course this is multiplied by negative 1 over s times du. Well, that's perfect. S is not a function of u, and so that can go out. A is not a function of u, so that can go out. And so then we simply get that this is equal to negative a over s integral u1 to u2 of e to the u du, which obviously is just simply equal to negative 1 over s e to the u evaluated from u1 to u2, but then we can just go ahead and substitute back on n, a to the s, e to the negative st evaluated from 0 to infinity. Going ahead and substituting in those limits of integration, we get negative, don't know why my negative sign didn't come through there. Okay, there we go. And then substituting in our upper limit, negative s infinity, minus our lower limit, e to the negative s times 0. Well, clearly this is going to go on off to 0, and this is going to go to 1. Or this is 1, because that is at a particular point in time. Infinity is kind of this notion of what happens as something keeps going and going and going. So then we get negative a over s, and then we have that being multiplied by negative 1. Since we have 0 minus 1, that's negative 1. And then last but not least, and I'll give it its own line, we have a over s. So for this particular function, the transformation comes across as a over s. But what does this mean? This is something that is very important to recognize, because this is telling us that when we are looking at this new space that we're calling either the S domain more technically correctly or the frequency domain, a little less technically correct, when we're looking at this new domain, when we are working with derivatives, taking the derivative or integrating, we get s's, we get multiplying or dividing by s's. When we look at functions, what are we ending up with? We're ending up with those functions coming across as multiplying or dividing by s's. And so in this particular space, we see that the representations for calculus-based functions, as well as functions themselves that we know and have transformed, functions themselves, they are coming over with similar forms. And so in this space, we start to see this merging of notation, of the notation associated with functions and with calculus-based operations. Now, we kind of started to get the sense of that with the annihilator, because it wasn't quite formally introduced that way. But what was the whole point of the annihilator? It was to wipe out a particular known function. What was the purpose of the linear differential operator, at least for our homogeneous solutions? It was to wipe out a differential, an unknown function associated with the differential equation. So the two were doing the same thing, but we called them different things. But you started to see that the annihilator is the same thing as the linear differential operator. One is just operating on a known function. The other one's operating on an unknown function. And their forms were essentially identical. So now we have completely formalized this idea that in this new space, we're dealing with a place where operations, specifically calculus-based operations and functions, their representations are merging together. And so that's very, very powerful, that we're now seeing these things that we considered to be separate and look separate in the time domain are now just different forms of the same stuff in the frequency domain. And so we started to see that a little bit, but now we can see it in much in a much clearer way. Let's just say it that way. So continuing with these different developments and examples of these developments, let's go ahead and take, so we took a look at the step function. Let me keep my indentation roughly about the same. So let's now look at the sinusoidal function. So for the sinusoidal function, what do we have? Well, now, of course, since we can go both negative and positive, we can go ahead and jump over there, and then we'll go over here, t, and we will have this coming across, and then we'll have the sine wave. Now, of course, that continues on off. So you can see that because we're dealing with the single-sided transform, we're going to constantly be dealing with values that are associated with time less than t equals 0. We're just going to say that those are 0. And so this particular function is captured by then f of t is equal to, let's just start with the 0 first, just like I did before. My apologies. Is equal to 0 for t less than 0, and it's equal to a sine omega t for t greater than or equal to 0. So with that, let's go ahead and work with the Laplace transformation then of this particular function. That's equal to, of course, f of s for this function. And so for us, and I'm going to need a little bit more room here. Actually, for this initial one, I won't. So I'll just go ahead and keep it over here. We'll have integral from 0 to infinity again of e to the negative st. And since it's 0 at time t less than 0, we just have to focus on the a sine omega t, and of course then dt. Now, looking at this, we might be thinking, wow, how in the world am I going to ever work with this? I got an exponential function multiplying a trigonometric function. Well, as we know, and so this will make things a little bit easier for us, as we know, the trigonometric functions can also be expressed in exponential form. And then we just have exponential functions. And of course, we know how to work with exponential functions. So from the different forms of Euler's equation, we have e to the j omega t is equal to cosine omega t plus j sine omega t. We also have e to the negative j omega t is equal to cosine omega t minus j sine omega t. And here I'm going to subtract these two. So if I subtract the two, what do I get? I get e to the j omega t minus e to the negative j omega t is simply equal to 0 plus 2j, right? So the cosines, when I subtract the two, they just go to 0. The sines then combine, so I get 2j sine omega t. And since we're working with sine in this particular case, that's exactly what we need. So that means, of course, that solving for that sine, I get that sine omega t is equal to 1 over 2j times that, times that combination of exponential functions, e to the j omega t minus e to the negative j omega t. So going ahead and substituting that on in, we have integral from 0 to infinity of e to the negative st times, so I'll just repeat a sine omega t dt, just to kind of lead this whole thing off. And that, of course, is now equal to integral from 0 to infinity of e to the negative st times 1 over 2j, my apologies, a over 2j. So let's go ahead and get that a in there. A over 2j, all of that multiplied by the combination of exponential functions. There we go. One with the positive argument, the other one with negative argument, all that times dt. So now let's go ahead. A is a constant, 2 is a constant, j is a constant, factor all that out, and then let's distribute across the exponential, this e to the negative st exponential function. And as we know, I'm just going to end up with an e to the negative st times e to the j omega t. Well, when I multiply two exponential functions together, I can just sum their arguments, and then the same discussion holds true for the other exponential function. So I'm not going to bother to show it multiplied out and then adding the arguments. Let's just jump straight to adding the arguments because we've seen that enough times. So I get an a over 2j times the integral. Sorry, that integral got a little funky on me. Times the integral 0 to infinity of now e to the j omega t minus st minus e to the negative j omega t minus st, all that times dt. And so then I can take each of these exponential functions and integrate them separately. So this is equal to a over 2j integral from 0 to infinity of e to the j omega t minus st dt. Here we'll go ahead and put that in set of parentheses, and then another integral e to, or sorry, 0 to infinity of e to the negative j omega t negative st times dt, close parentheses, close square brackets. And as we saw before, we can just deal with this using u substitutions. So here I'll just show you the u substitutions, and then I'll let you know what the substitution values were in just a second. So let's go ahead and just say that we already know that we're going to be dealing with integral from u1 prime to u1 double prime, and that's going to be e to the u1 times 1 over j omega minus s, all that times du1. And let's go ahead and put this in parentheses. And then minus, and we're going to have a similar structure. Here we'll just have our limits u2 prime, u2 double prime, and we'll have e to the u2. And now we're going to have a negative 1 over j omega, this time plus s, and then all that times du2. And here I'll just close the parentheses, scroll that over, and close parentheses and brackets. And so here you can see, so now I'll do our where. Just for completeness, I think you've seen this form enough times, but let's just go ahead and mention that here I've now said that U1 is j omega minus s times t. du1 is, of course, equal to that same quantity now times dt, and then solving for dt, that's just simply going to be equal to my 1 over j omega minus s times du1. And so then you can see that's where this is coming from right here for my dt. So that's what I ended up with for dt. And then a similar structure for the u substitution. Here I've now factored out the negative sign, and so now we get a j omega plus s times t. For our u substitution, du2 is of course now the same quantity times dt, and then last but not least, solving for dt for the second integral, we just get a, here I'll do the -1 up here, j omega plus s in the denominator, all that times du2. So that's what I substituted in. And so now working with those particular expressions, clearly, oh, don't know why I did that, sorry. Hopefully I can get it back to about the original. It looks close enough. So we'll just run with that. So clearly this 1 over j omega minus s is a constant. This -1 over j omega plus s is a constant. So we can factor both of those out. And then we're just left with e to the u1, integral of e to the u1 du1, e to the u2 times du2, and integrating that, of course, we're just going to end up with e to the u1 and e to the u2 for both of those. So let's go ahead and capture all of that. And so I get a over 2j, and then for the integrals, we get e to the u1 evaluated from u1 prime to u1 double prime. All that multiplied, and here I'll put the constant on the backside, 1 over j omega minus s. And then we have a negative, so here I just brought out that explicit, I brought out that, I didn't bring out the negative sign. My apologies. We always had a minus sign there. So that's just the same minus sign. I thought I factored it out, but I haven't yet. And then we have e to the u2 evaluated from u2 prime to u2 double prime. And so again, I still haven't factored out the negative sign, so we just hold on to that. -1 over j omega plus s. Close brackets. So now back substituting in for our u's, a over 2j, e now to the j omega minus s times t, all that multiplied by 1 over j omega minus s. And now I did factor out the, one thing I need to do, my apologies. I need to bring in my original limits of integration, 0 to infinity, and then I can include my 1 over j omega minus s. Now I did factor out the minus sign and cancel it with the 1 out in front. And so then we have plus e to the negative j omega plus s times t. All that evaluated from 0 to infinity, and now that's multiplied by 1 over j plus s. So now let's look at these limits of integration. And I'll apologize in advance. This is where things get a little long because, of course, now I have to bring in those limits or substitute in those limits of integration. So we get a over 2j. And so then we get an e to the j omega minus s times infinity, or all that times infinity, minus, so that's our upper limit, evaluating our upper limit. Now let's evaluate our lower limit, minus s times 0, and all of that. Now it looks like my j got a little funny there. I apologize. Let's clean that up. And then all of that, of course, multiplied by our constant 1 over j omega minus s. And then all of that added on to e to the negative j omega plus s times infinity minus e to the negative j omega plus s times 0. All of that times 1 over j omega plus s, and then close our square brackets. So when I look at these particular quantities, clearly whatever this is, I'm going to multiply it by 0, and I'm going to get e to the 0. That's just going to be 1. So both of these second terms are just going to become 1. The question comes up, what in the world's going to happen with these first terms? What's up with that? Well, we can see from what we know that if I look at, so again, I'm summing together things in the argument of this exponential function. That means that I can go ahead and have two exponential functions multiplied together. So I get an e to the j omega infinity times e to the negative s infinity. So am I of exponential order? Am I not? What's going on here? Well, let's think about it a little bit. So that can clearly go to 0. But when I look at this particular quantity, what's that quantity doing? Well, that's a purely imaginary exponential function, or an exponential function that has a purely imaginary argument would be a more correct way of saying it technically. But what do exponential functions with purely imaginary arguments do? They oscillate. That's all they do. They don't grow to infinity. They don't go to 0. They just oscillate. Well, an oscillating function is clearly going to be captured by the exponential order argument because it's nowhere close to even exponential order, so it's within the bounds of that argument. And so clearly, this is going to go to 0. And so that means that these two first terms are both going to go to 0 because I got an oscillating term multiplying an exponentially decaying term. Clearly, we're going to end up with everything going to 0, exponentially decaying to 0. And so I get an a over 2j times 0 minus 1 times j omega minus 1 over j omega minus s plus 0 minus 1 times 1 over j omega plus s. Clearly, I'm just going to get a negative 1 here, a negative 1 here. I can go ahead and factor that on out. So this is equal to now just negative 1 times a over 2j 1 over j omega minus s. But as we saw from our discussion of complex numbers, I don't like having complex numbers in the denominator, so let's go ahead and I'll multiply this by j omega plus s. I'll multiply, so denominator multiplied by that, numerator multiplied by that, plus s. And then we have j omega plus s, and now I'll multiply by j omega minus s. And so we can see that we get a real number, oh, my mistake, we don't get a real number in the, we do. My apologies. Whew. For a second there, I thought I misspoke. So we'll get a real number in the denominator, with s being a parameter still. Though we'll see that s is a little complicated in and of itself, but we won't have any j's. So let me say it this way. We won't have any j's explicitly appearing in the denominator. And we're going to have a common denominator. So that's the nice thing about this particular operation. And so then we can say, okay, this is just negative, so I'll get rid of the -1 up in front there and just give it a, reference it as a negative sign. And then we get a j squared times omega squared minus s squared after I multiply all that on out. And since I have a common denominator, I can just add everything in the numerator. So I get a j omega plus s plus a j omega minus s. And so we can see that clearly the s's are going to cancel in the denominator, and I get this being equal to negative a over 2j. And then what am I going to get? I'm going to get a 2j in the numerator, 2j omega to be a little bit more precise. And then I'm going to get a j squared in the denominators, -1 specifically, times omega squared. Come on, there we go. And then we have a minus s squared. And so then we can go ahead and cancel the 2j's, denominator, numerator, and then we also have this negative sign that this -1 I can factor out in the denominator, and I can cancel it with the -1 in the quote unquote numerator, if you want to call it that. And so we can see that we just end up with a omega over omega squared plus s squared. And that's the transformation for this particular trigonometric function for sine. So again, what can we see? It took a little while to get there. It wasn't too bad though. But we can see then, again, that we're just dealing with s's. In this case, s is again in the denominator, but we're just dealing with s's. That's it. And so again, we can see that this particular transformation allows us to express functions that we know with these s's and functions that we have yet to find associated with the differential equations, we can see those being multiplied by s's. Now, before I go into one more example, I want to note that, again, I said that this transformation leads to a merging of our idea of characteristic equation and linear differential operator. And why do I say that? Well, we're already starting to see some of the linear differential operator coming in here in terms of multiplying by a parameter whose power represents the order of the derivative. So we're already seeing that, and we're also seeing this kind of annihilator idea coming in, because of course the annihilator is going to be associated with what we have going on there, specifically in the denominator. And so we can see the linear differential operator thread coming in here. But remember, the linear differential operator, the capital D was an operation. It was not a value. It was not a parameter itself. Unlike in the characteristic equation approach, where S was a variable that could take on, or a parameter that could take on values. Here we have the best of both worlds. S can take on values, but it also represents what's going on with the derivative, or in this case, also what's going on with if we integrate something. So it's capturing everything. It's rolling both what we were doing with linear differential operators up with what we were doing with that assumed solution approach that led to the characteristic equation. We're rolling all that up in this particular development, in this transform. It captures it all. So I'm hoping you're starting to see the power, because again, S can take on values. And it turns out it's actually a complex. That's why I had to be a little careful when I was talking earlier. It can actually be a complex parameter. It can take on complex values. So it's important to see what's going on here. This particular transformation and this space that we get from this transformation is exceedingly powerful. It's exceedingly rich. It's a really amazing mathematical world to play within. Again, if you want to call it that, it's an amazing mathematical framework. And so hopefully you're starting to see that, where it's really interesting, where we're now going into this world where before we thought functions were functions and operations were operations. And now we're going into this world of, oh, well, functions are just going to have S's in them. Operators are going to be represented by S's. And everything just kind of merges together in this particular space that we're dealing with. Functions and operations merge together. So it's very interesting and very, very powerful. Let's now, and where did we have? Okay, there we are, sinusoidal function. So let's now do one, or figure out what's going on with one more function, which is the exponential function. So just like all of the other functions, for this single-sided Laplace transformation, we'll have our exponential function, t, u, and we'll come on in, and then our exponential function will take off from there. So when we look at this exponential function, so it'll be 0 at times less than t equals 0, and it will be captured by the exponential function at times greater than t equals 0. And here, even though I didn't show it, there is, of course, going to be a little step there. And so this is going to be captured by f of t is equal to 0, and then e to the, let's just say at in this particular case, for 0 for t less than 0, e to the at for t greater than or equal to 0. So again, let's just start off with our general notation. So we have the Laplace transformation of f of t is equal to f of s, of course, and then for our particular case, we have integral from 0 to infinity of e to the negative st e to the at, all that times dt. And so you can see how simple this particular transformation is going to be, especially considering what we just did on the last one. So integral 0 to infinity of clearly e to the negative st plus at dt. And so then we can go ahead and so we can do a u substitution, u equal negative s plus a times t. So here I just factored out the t, if everybody's okay with that. And then my du is going to be equal, need an equal sign, is going to be equal to clearly negative s plus a times dt, and then just solving for dt to substitute back in, I get that this is equal to 1 over a minus s times du. So substituting that back in for dt, and now I'll explicitly factor out the t and the argument for the exponential function just to make it a little bit easier to see. So then this d, here I'll just kind of do these dots showing that I'm just kind of skipping over that little discussion that we had. And this is equal to integral u1 to u2 of 1 over a minus s e to the u du. And then going ahead and clearly factoring out the 1 over a minus s, because that's constant with respect to u, we get, and then we just have integral u du, we just get e to the u evaluated from u1 to u2. Now, going ahead and transforming back and bringing our t's back into play, this is clearly going to be equal to, so that's not going to affect the constant out in front, so we're going to get an e to the a minus s times t evaluated from 0 to infinity. Now, let's go ahead and use that property of the exponential function where I can represent this as two different exponential functions, 1 over a minus s, e to the negative st, e to the at, integrated from, or evaluated at 0 and infinity. I've already integrated it. And again, going ahead and capturing that 1 over a minus s. Now we have e to the negative s infinity e to the a times infinity minus e to the negative s0 e to the a0. Of course, both of these are just going to yield a 1, and so 1 times 1 is 1, and I get a total of negative 1 from there. And then, of course, from our exponential order argument, this is going to be equal to 0, exponential order, since that has exactly the form that we need for exponential order. So then, clearly, we get that, I'll skip one more line, 1 over a minus s, and then all of that times negative 1. Well, I can factor out a negative 1 from the denominator, in which case I just get s minus a. And so we can then see that for our exponential function, we get an s minus a. And again, if we replaced s with a capital D, you'd recognize that this is related to the form of the annihilator for the exponential function. So let's go ahead and box that up. And there we go. So I hope that through these examples, you've started to get a sense for the power of the Laplace transformation. One of the most immediate things, well, one of the expected things is, of course, as we operate on functions using calculus-based operators, i.e. taking the derivative or taking the integral, we are effectively multiplying or dividing by s's, but also hopefully something you saw that I told you about, but you actually saw it coming right out of the development and was pretty cool, was that you're also able to capture what's going on with the initial conditions as promised. I also promised that this would help us take care of the particular solution, and that's exactly what we saw when we started transforming these specific functions, is that we can then represent these functions in this transformed space, and that's going to capture the particular solution as well. So we get the differential equation, we get the initial conditions, we get the particular solution as well from this framework. But one of the other things that I've been emphasizing, and I hope you're starting to see that in this particular space, in this, using this transformation and in the space created by this transformation, all of a sudden the distinction between these calculus-based operations and how we represent those operations and how we represent functions are now blurred. Actually, more than blurred, they're almost completely eliminated. Where now functions look just like calculus-based or are represented in ways that appear to be exactly like calculus-based operations, and calculus-based operations look like they're being represented just like a function is being represented. And that isn't a huge surprise, because with our discussion of annihilators and linear differential operators, we started to see that merging, that blending of representations. But now this transformation has definitely formalized it. And now we can see where we're in this space where functions start looking like operations and operations start looking like functions. And that leads to a very, very powerful place within which to work. So hopefully you can see that. And of course, as we keep working with these concepts, I think you're going to see it become even more apparent how powerful this space is. So with that, I will call this video lecture, oopsie, got a little rambunctious there. I will call this video lecture a wrap.